Alrighty, hello. This is going to be the notes for the second half of 12.5. And now we're going to specifically focus on planes in 3 dimensions. Okay? So I'm going to go through, just kind of, let's see if we can figure out the equation for a plane first of all. So let's say we have a plane. And on this plane, there's a vector. Looks something like that. And let's say we have a point x naught, y naught, z naught at the beginning of that vector. And let's say over here we have just x, y, and z. I'm just going to use that instead of x1 and y1 and z1. All right, so there's a vector that's on a plane. Now, let's go ahead and throw in, we talked about this a little bit yesterday, or the previous section, a vector that's normal to the plane, meaning that the plane and the normal vector, which is in red, those are going to be orthogonal, okay, or normal. That would be the word that we use when we're talking about planes. And let's go ahead and say that that normal vector has components A, B, and C. All right. Well, we know that since, well, really any vector on the plane is going to be orthogonal to the normal vector because it's normal to the plane. So anything, any vector on the plane must be also perpendicular. Then we know that the dot product of n with the purple vector, let's just call that, let's go ahead and just write the components. So that's going to be x minus x naught, y minus y naught, and z minus z naught. Okay, so the purple vector dotted with the normal vector. Let me go ahead and just kind of write that out now. So that's going to be A, B, C dotted with this purple one. Let me write that down again. We know that this dot product has to be 0, right? Because if the vectors are orthogonal, the dot product has to be 0. So I'm going to go ahead and just write out what that dot product looks like. So that's going to be A times x minus x naught plus B times y minus y naught plus C times z minus z naught. And then that has to equal 0, right? That has to equal 0. Well, here is your plane equation. This is actually called point normal form. Kind of analogous with point slope form, similar to what we did in 2 dimensions, but we call this point normal form. And in order to use this form for a plane, you need to have a point on the plane, which is going to be x naught, y naught, z naught, okay? The x, the y, and the z you're just going to leave, right? But then you also need, in addition to one point, you need a normal vector. And here we are, okay? And so as long as you have those, and really you could have used either of them, either of those points, you get your plane equation, okay? Now in standard form, if you distribute everything out and group everything, you're going to get ax plus by plus cz, and we can lump, so if I multiply a with the x naught, b with the y naught, and so on, those are all going to be constants. We can lump all of those together into one new constant, which is d, okay? But the most important part is that whether the plane equation is in point normal form or in standard form, okay, that the coefficients of x, y, and z, okay, give you the normal vector, okay? the coefficients of x, y, and z, whether it's in point normal form or standard form, represent the components of the normal vector. Okay, so now we're going to run through various, lots of examples. There's lots of different things that could be asked in this context about planes, and we're going to do several of them. Hopefully that'll cover most of what you need. All right, so first example, let's say we want to find the equation of the plane through the point 3, 1, negative 7, and perpendicular to the vector 4i plus 2j minus 5k. Okay, so 4i plus 2j minus 5k and 3, 1, negative 7. All right, if you know what you're doing, as usual, pause it, write the solution out, and then check. But here we go. So we have a point, we have a normal vector. We can go ahead and just plug everything in to the point normal equation up here. And so that's going to be 4, because the a, this is your a, your b, and c in the normal vector, right? So it'll be 4 times x minus, and the only point we have to use here is 3, 1, negative 7. So you just plug that in. And set it equal to 0. This would be the equation in point normal form. Oop, just caught something. Accidentally switched these. This should be minus 5, and this should be plus 7 in here. Sorry about that. Okay, the components are 4, 2, negative 5, so that's the a, the b, and the c. And now we're looking good. Okay, so that's the equation in point normal form. In standard form, you are going to just distribute everything out. So you're going to get 4x plus 2y minus 5z. And then if you combine all your constants here, let's see, you got negative 12, negative 2, that's negative 14, and then, so that should be, let's write that out. So negative 12, negative 2, and what is that, minus 35? So that's going to be minus 49 equal to 0. Okay? All right. So hopefully that makes some sense there. Sorry, I just didn't want to write out the whole calculation, and so I just kind of did that off to the side there. All right. Next example. Let's say we want to find the standard plane equation for the plane containing these 3 points, 2, 1, 1, 0, 4, 1, and negative 2, 1, 4. Okay, so again, if you kind of have an idea of what you got to do, try it out and check your answer. All right, so first what we're going to do is, well, obviously we have 3 points available, so that's not a problem. The problem is we don't have a normal vector. So imagine this is our plane, and here are the 3 points, okay? We need a normal vector. So what we can do is, if we create 2 vectors here, so maybe from point number 1 to point number 2, and then point number 1 to point number 3, okay? If we take the cross product of those 2 vectors, now we have our normal vector, okay? So that's all we have to do. So let's go ahead and create two vectors. So we're going to, and then we're going to cross those. Okay, so if I go from first point to second point, I'm just going to write that vector in component form. So that'll be -2, 4 minus 1 is 3, 1 minus 1 is 0. And then we're going to cross that now. And again, I'm going to go first to third. You don't have to do those. You can do second and third. It doesn't matter. But if I do that, put that in component form, -2 minus 2, that's going to be -4. 1 minus 1 is 0. 4 minus 1 is 3. Okay? And so now if I take the cross product, set that up as we discussed earlier as a determinant. And let's go ahead and find that out. So what's that going to be? So the I component is just going to be 9 minus 0, so 9. The J component will be -2 times 3, which is -6. And we do the opposite, right? So that's going to be +6. And then the K component will be 0 and then minus -12. So that's 12 there. Okay? And so there's our normal vector. So first we find our normal vector. And now we have the normal vector, and we can pick any of those 3 points. And so I'll just go with the first one. So we're going to have 9 times x minus 2 plus 6 times y minus 1 plus 12 times z minus 1. And that equals 0. Now if we want this in standard form, you're going to want to distribute, and actually just to make my life easier, since I don't have my calculator here, I'm going to reduce this. I'm going to divide everything by 3. So this is now going to be 3x minus 2. And I suppose you can do that here, right? This is going to be the same as 3, 2, 4. As long as you have a multiple of the normal vector that you find from the cross product, it's still orthogonal to the plane. The dot product will still be 0. So you can always reduce the coefficients here just to make things a little easier. All right, so if I distribute that out, that's going to be 3x plus 2y plus 4z. And then I get -6, -2, that's -8, -4, that's going to be -12. And so there is the plane equation in standard form, given the 3 points. And this is a pretty typical Calc 3 find the plane equation question, right? Where you don't have the vectors given to you. You have to kind of find the vectors on your own, take the cross product to find the normal vector, then you can use the plane equation. Okay. Going on to, let's see, another application. Find the intersection of the line x equals 3 plus 8t, y equals 4 plus 5t, and z equals -3 minus t. And the plane, so here's a parametric version of a line in 3 dimensions, and our plane equation is going to be x minus 3y plus 5z equals 12. Okay, so again, try it if you know what's going on, and if not, that's okay too. How's this? Okay, so here's the solution. Probably the easiest thing to do is to just let x naught, y naught, z naught be the solution, be the point of intersection. And so now what that means So what that means then is that this point has to work in the plane equation, right? If it's the solution, that means that it's not only on the plane, but it's also on the line. So let's start with the plane. So that means x naught minus 3y naught plus 5 times z naught. Well, that has to equal 12 for some value of t. Okay? And so, but we also know what x naught, y naught, and z naught are in terms of 3, right? So we're going to say x naught is just going to be 3 plus 8 times t naught. Y naught is going to be 4 plus 5 times t naught. And z naught is just going to be, where is it? Negative 3 minus t naught. Okay, and so now if you go ahead and replace those into the equation, you get 3 plus 8 times t naught minus 3 times 4 plus 5 times t naught plus 5 times negative 3 minus t naught. That's going to equal 12. And in the interest of time, I'm just going to say we get that the t value here, after you distribute combined like terms and get t naught by itself, you get negative 3. Okay, so now what is the point of intersection? Well, we know what the point is going to be based off of the coordinates of the line, right? So that's going to be the easiest thing to do. You're just going to plug 3 into there. So the point is going to be 3 plus 8 times negative 3. And then we got 4 plus 5 times negative 3. And negative 3 minus negative 3. And so when you do that, you get negative 21, negative 11, and 0. And so there's your point of intersection. Okay? All right. Let's try another example here. Find the equation of the line of intersection. Oh, and I forgot to mention, so you don't have to be so formal for this previous example where you're like, okay, we're looking for the solution, let's call it this, let's plug it in, then this needs, I mean, you could have literally just gone back in and just done, okay, if this is x, I'm going to put that in there. If this is y, I'm going to put that into the y. And if that's z, you put that in there. You get your t value, which is going to be obviously negative 3. And then you can just replace back into the parametric equation of the line to figure out what point the solution is going to be. Okay, so that's probably what you will end up doing. Okay, so with this example, we're finding the equation of the line of the intersection of two planes. And let's say we have x minus 2y plus z equals 0, and 2x plus 3y minus 2z equals 0. Now, if you're wondering, what do we mean find the equation for the line of intersection? Remember, if two planes intersect, assuming they're not parallel, then we're going to have something that maybe looks like this. So here's, imagine, we got this plane here, and this plane over here. And, I mean, these extend, obviously, infinitely in every direction, but you can see that they meet at this edge, which will form a line, and that's the line of intersection. Imagine, it's like the binding in your book, right? When you open up the book, you got two planes, basically, and where the two planes meet, that's the binding. That would be the line of intersection. So now how do we do that? How do we find what that line is going to be? Well, one option, okay, would be to just try to solve. This is a system of equations. It's two equations, three unknowns. If we had a third equation, we could potentially have a single point as the intersection, but you're still going to treat this like a normal system. So one option would be to maybe use elimination. I see that if I multiply, let's say I multiply this first equation by 2 and then subtract, that will eliminate my x terms. And so now, what do I get there? Oh, better yet, if I just add, let's do that. If I add, I get the z's to cancel out. And so now I get 4x. And when I add there, you get minus y, and then that's going to equal 0. And so this kind of represents the equation for the intersection. So now how do we write it out? We want to write this in parametric form, okay? And so anytime you have two variables and we're going into three variable parametric equation, right? You can let x, like if you know what the formula is for y, let x represent t. So there's the first parametric equation. Then y is just going to be 4 times x, which is going to be 4t. And now to find z, we can go back. Let's maybe use the first equation here. Go back in there, replace x with t, replace y with 2t, so that's going to be minus 8t. And then now we got plus 2z equals 0. We want to get z by itself, so 2z is going to be 7t. Oh, sorry, I was looking at this green 2. This is just a z. And so after you plug in your x and y definitions using t's into the equation, you get t minus 8t plus z equals 0. Made a mistake there. There was no 2 there. I just kind of saw the green 2 for some reason. Anyway, once you get z alone, move everything into the other side, you get 7t. And so this is the parametric equation for the line. Okay. The last topic that's in this section is, and again, I'm highlighting what I think is going to be crucial. There are obviously lots of other questions that can be asked, and you might even see some different types of questions in the homework and in the packet. And so those you're going to try to figure out with what you know already, and obviously if we can't figure those out, then you can ask and we can work on them together. All right, so the last topic in the plane equation section is distance, okay? Distance. And it all kind of generalizes back to point to a plane. So we're going to start with that. So imagine we have a point, let's call it P, and we're trying to find this distance, right? The shortest distance, not just a random segment from P. It's got to be normal to the plane, okay? And so probably the easiest thing to do would be to have you guys maybe pull from your memory bank from a few years ago in pre-calc. So this is analogous to the point to a line formula. In pre-calc, you had a point, you had a line, here's P, right? Same thing. The formula for this distance from a point to a line was just the absolute value of a x naught plus b y naught plus c all over the square root of a squared plus b squared. And this is assuming that this equation is written in this format, ax plus by plus c equals 0. So you have a standard form of an equation set to 0. That's where these coefficients a, b, and c come from. X naught, y naught would just be this point, the point of interest, and that's it. Okay, so for point to a plane, it's the same exact concept. You just extend it to 3 dimensions. And so now we have x naught, y naught, z naught for our point, and our plane equation is going to be the standard ax plus by plus cz plus d equals 0. Okay, and so now that distance from a point to a plane, very much like the purple one, will be the absolute value of a times x naught plus b times y naught plus c times z naught plus d all over the square root of a squared plus b squared plus c squared. Okay, so a couple of quick examples in using this concept. Let's just do a straightforward computation. Let's go ahead and find the distance between, let's say, Q, which is at -154, and the plane 3x minus y plus 2z equals 6. One second here. There we go. Okay. So, what do? Well, we pretty much have everything we need. The only exception is that, remember that this needs to be set to 0. So really what we're going to do is move the 6 over, and then we have all the all the coefficients ready to go, and we can just now plug in, here's our x naught, y naught, and z naught. Okay, so distance will just be the absolute value of 3 times -1 minus 1 times 5, and then plus 2 times the z coordinate, which is 4. And now again we subtracted 6, and now we do the square root of the coefficients, the sum of those squared, so that'll be 9 plus 1 plus 4. And so simplify. Let's see, up here you get 3 minus 5 plus 8 minus 6, absolute value of that should be 6. And then here we get root 14. And so this would be the distance from this particular point to this plane. Okay, so that's your straightforward, you just plug everything in pretty much. Not too difficult. Now let's step it up a little bit and see what happens if we want to find the distance from the plane 3x minus y plus 2z minus 6 equals 0. And let's do 6x minus 2y plus 4z plus 4 equals 0. And so these are parallel planes, obviously. The coefficients are just multiples of each other, so it's the same plane, just slightly different location based off of this constant at the end. And so here's a visual. Right, here are two parallel planes. Now, we don't know how to find the distance from a plane to a plane, but what I do know how to find is the distance from a point to a plane. So if I just pick any old point, so pick a point on the first plane, now I have a point, and I already have the plane equation for it below, and we're done. So it's actually pretty easy. You just need to create your own point. Um, and so if I'm using, this is my plane 1, plane 2. If I'm looking at plane 1, the easiest point would probably be, just set 2 out of the 3 variables equal to 0, and then solve. So for example, if I get x, you're going to get 2, 0, 0, right? So in other words, I found the x-intercept. That's a pretty easy point to find. So is the y-intercept. You could have done 0, comma 6, or 0, comma negative 6, comma 0. If you choose to do the z-intercept, you'd have 0, 0, comma 3. It doesn't matter. It's all going to work out just the same. But here's your point. And now 2, you're just going to use the distance formula to plane 2. So now we can just plug everything in and we're good to go. So the distance is going to be absolute value of, and now here's plane 2, so I'm looking at this equation, 6 times 2 minus 2 times 0, and you probably don't need to write that, but just for completion's sake, I'm going to write everything out. And then we do the square root of 36 plus 4 plus 16. Simplify that. 12 plus, these go away. 12 plus 4 is 16. Down here we get root 56, which I guess we can reduce that. Root 56 is the same as 4 times. So that's 2 root 14. So I'm getting 8 over root 14 for the distance. I suppose that would have been easier. I could have divided this equation by 2, and then it would have been the same result in one less step, I suppose. But either way, not too bad of a calculation. All right, so that's still using the point to a plane concept, but we started with now 2 parallel planes, right? So now you just reduce it to a point to a plane, and then you just do exactly what we've been doing. Okay, now let's step it up one notch further. This is the last problem we're going to do. All right, let's say we have, and so I'm going to categorize these. So this example that we just did was 2 parallel planes. And this example is going to be 2 skew lines. Okay, so find the distance between the skew lines below. Here they are. So for line 1, we're going to have x equals 1 plus 4t, y equals 5 minus 4t, and z equals negative 1 plus 5t. And for the second line, we're going to have x equals 2 plus 8t, y is going to be 4 minus 3t, and z is going to be 5 plus t. Now you don't have to prove that they're skew like we did earlier. We're told that they are, so we're going to assume we have skew lines. Okay, and probably the easiest way to visualize what we're going to do is to draw a picture very similar to the previous example. Okay, if we have 2 skew lines, you can imagine that we have 2 parallel planes and that we just have a line on one plane and a line below over here. So these lines are skew. They don't intersect because they're on parallel planes. And we're looking for the distance between these 2 lines, basically. So pick a point here, go straight down. Let me call this point Q1, and let me call this point Q2. Okay? And so here's the distance that we're trying to determine. All right. So now, oh man. Sorry, the Elmo's not cooperating with the, anyway. So here we go. So to find the distance between these two skew lines, we're going to do something similar to the previous example. We've already kind of set it up. First thing is you're going to pick a point on the first line. So that would be my Q1. So probably the easiest thing to do here would just maybe let t equal 0 in the first equation. Okay, because you're picking any point, and that's probably the easiest one to calculate. And so my Q1 is just going to be 1, 5, -1. So that's the first step. And so we're basically going to find the distance between this point and this plane now. Okay. Well, that's the problem is, what is the plane equation for this second plane, right? What's the plane equation? I don't have a normal vector, I have a point, okay? So I would first need to find a normal vector, so that's step 2. Find a normal vector to second plane. Well, and really, let's write it out. Let's find the normal vector of both planes, right? If they're parallel, they can share the same normal vector. And that's actually pretty easy to do once you see it. If these lines are parallel, you can imagine that this purple line can get translated downward so that it's on this plane. And so what that means then is if you take purple vector and red vector, take the cross product, you will now get a normal vector to not only plane 1 but also plane 2, which is what we really want to find. Okay? And so we have those vectors, right? Remember that for the lines, these coefficients right here, 4, -4, and 5, and then 8, -3, and 1, those are the components of a vector that is on line 1, and then the components of a vector that's on line 2. Okay? And so all we need to do is take the cross product of those two vectors, so 4, -4, and 5, and we cross that with 8, -3, and 1. All right, and so now if you do that, in the interest of time, you guys hopefully now are pretty competent with finding cross products. You should get 11, 36, and 20. Okay, so now we have a normal vector. We got a normal vector over here, right? Actually for both planes. We got it figured out. And so we should be pretty good to go, because now we just need the plane equation. So that's actually step 3. That's easy. So what's plane 2 equation? Again, this is plane 1, this is plane 2. What's the second plane equation? Well, here's my normal vector, and now we just need a second point, or need a point on P2, so we can use any point from the second line. Okay, so pretty straightforward. Just like the first line, we picked any point, we let t equal 0, we can do the same here. So if we let t equal 0 for L2, now I get my second point. We'll call it Q2, and if I plug that in, let's see, what are my equations over here? If you plug 0 in, you should get 2, 4, and 5 for the coordinates of that point. And so the plane equation for the second plane, using the point normal form, so we're going to use normal vector. Here's our point. And so now we have 2 times x minus 11 plus 36 times y minus 4 plus 20 times z minus 5. That equals 0. Okay. So clean this up, write it in standard form. Okay, I'll let you guys kind of finish that, but here's what it looks like in standard form. It'll be, oh shoot, I did that again, didn't I? This should be 11, and this should be 2. I'm sorry, guys, I keep flipping my numbers here. 11, 36, and 20 are the coefficients, and then we got 2, 4, 5 as the coordinates. Okay, so once you distribute that all out, you get 11x plus 36y plus 20z minus 266 equals 0. Okay, and you're pretty much set up now. So finally, use distance from first point, which was Q1, which you have above, to plane 2, which we have right here. This is my plane 2 equation, right? So I won't do that for you guys. You guys should be able to set that up now, but here is the answer so you can check. It is going to be 95 over the square root of 1817. Okay? And so there you have it. Lots of different applications dealing with planes. We'll see you guys next time.